Fine, let's start. Number 1. The devil worm. Picture an animal living inside solid rock, more than a kilometer beneath your feet, in water that has not touched the surface for thousands of years. For most of scientific history, this was thought to be impossible. Animals need oxygen, food, and space, and the deep crust seemed to offer none of these. Then, a drilling operation at the Beatrix gold mine in South Africa changed the rule. From fracture water flowing out of deep boreholes, researchers pulled up a worm. It was tiny, only about half a millimeter long, but it was a true multicellular animal, not a microbe. They named it Halocephalus mephisto, after Mephistopheles, the demon of the underworld in the old Faust legend. The press simply called it the devil worm. The work was led by Gaetan Borgoni of Ghent University and Tullis Onstad of Princeton, and it was published in the journal Nature in 2011. The team recovered the worm from depths between roughly 900 meters and 3.6 kilometers. To be certain they had not simply dragged a surface creature down the hole, they dated the water using isotopes. It came back at 3,000 to 12,000 years old. They filtered tens of thousands of liters of borehole water to find their specimens. They ran carbon-14 tests to rule out contamination from the mine itself. What they found rewrote the limits of life. The worm tolerates temperatures up to about 37 degrees Celsius. It survives in water with almost no dissolved oxygen. It feeds on the films of bacteria that coat the rock fractures, grazing an invisible pasture in total darkness. Some populations reproduce without males, which lets a single individual colonize an isolated pocket of water on its own. Why does this matter beyond the strangeness of it? Because before this, the deep biosphere was thought to be bacteria only. A follow-up study in 2015 found an entire hidden community down there, including flatworms, rotifers, and tiny arthropods. The deep earth was not sterile. It was inhabited. The mainstream reading is simple deep biosphere ecology, life adapting to extreme isolation. The astrobiology reading goes further, treating these worms as a template for what might survive beneath the surface of Mars, or inside the icy moon Europa. And at the speculative edge, some thinkers fold this into panspermia, the idea that life could ride between worlds and shelter deep underground. Onstad's own work fed directly into NASA's astrobiology program. The unsettling truth is that we only know any of this because a drill went looking for gold and found something alive instead. And the water that worm swims in turned out to be even older than the worm itself. Number 2. The oldest water on Earth. If the devil worm was disturbing, the liquid around it was stranger still. At the Kidd Creek mine near Timmins, Ontario, one of the deepest base metal mines on the planet, water flows out of exploration boreholes that turned out to be ancient beyond anything previously recorded. Barbara Sherwood Lawler of the University of Toronto and her colleagues first reported in 2013 that this water was at least 1.5 billion years old. Then, in 2016, from a fracture near 2.9 kilometers down, they found water dated to roughly 2 billion years. It is the oldest water known anywhere on Earth. How do you date water? Not the hydrogen and oxygen themselves, but the gases dissolved in it. As rock decays radioactively over eons, it releases helium, neon, argon, and xenon, which accumulate in trapped water at a steady rate. Measure those noble gases, and you can read the clock. The numbers doubled the previous record for isolated subsurface water in a single stroke. Sherwood Lawler did something most scientists would not. She tasted it. She described it as extremely salty and bitter, far worse than seawater. That fits the chemistry. Billions of years of reaction with the surrounding rock left it up to 8 times saltier than the ocean. The real shock is what the water can support. It carries dissolved hydrogen, produced when natural radiation splits water molecules apart, a process called radiolysis. That hydrogen is food. It feeds sulfate-reducing microbes that live with no sunlight at all, drawing energy purely from chemistry. The Precambrian rock of the Canadian Shield sealed this water away like a closed jar for 2 billion years, and inside that jar, chemistry kept running and life hung on. The mainstream geochemical view treats this as a natural reactor, rock and water making fuel in slow motion. The origin of life community is more excited because this same hydrogen-rich, sulfide-rich chemistry resembles deep-sea hydrothermal systems where life may first have begun. At the fringe, you will hear it framed as a kind of preserved primordial Eden, a sealed remnant of the early Earth. The research is funded through programs like the Deep Carbon Observatory, and its clearest practical lesson points off-world. If water can stay liquid, salty, and habitable underground for 2 billion years here, the same could be true beneath the surface of Mars. A mine in Ontario became a time capsule, but not every drill that reaches deep brings back something cold and slow. Sometimes it brings back fire. Number 3. The Iceland Magma Strike. In 2009, a drilling crew working on the Iceland Deep Drilling Project set out to do something fairly ordinary for Iceland. They wanted to tap superheated geothermal fluids to generate electricity. The well, called IDDP-1, was being drilled at the Krafla volcano. At about 2.1 kilometers down, the drill stopped making sense. It had struck magma, molten rock, directly. This is almost unheard of. In the entire history of drilling, boreholes have intersected magma only a handful of times, at Kilauea in Hawaii and at Menengai in Kenya. The magma at Krafla was rhyolitic, sitting at a temperature near 900 to 1,000 degrees Celsius. Molten rock actually flowed up into the borehole and froze into volcanic glass inside the drill string. The planet had reached up the pipe. Most teams would have abandoned the well. Instead, the engineers did something audacious. They finished it, turning IDDP-1 into the hottest geothermal well in the world. It produced superheated steam at around 450 degrees Celsius. The estimated output reached roughly 36 megawatts of electrical capacity from a single well, far beyond what a normal geothermal well delivers. In effect, they had proven the concept of magma-enhanced power, drilling close enough to magma to harvest its heat directly. It did not last. The volcanic gases coming up the well were acidic, and they corroded the wellhead until the experiment had to be shut down. But the scientific payoff was enormous. Geologists rarely get to study the roof of a magma chamber. Here, magma had been found far shallower than anyone predicted, and the quenched glass that came up the drill could be analyzed for its exact composition and gas content. The mainstream framing is geothermal engineering. A lucky accident turned into a power breakthrough. Volcanologists read it as a rare natural experiment, a direct probe of shallow magma that improved hazard models for the whole region. The more speculative voices imagine a future of magma observatories and magma-powered grids, and that future is already taking shape in the proposed Krafla magma testbed, a plan to drill back into the magma on purpose to study it in place. A later well, IDDP-2, reached 4.6 kilometers and tapped supercritical fluid near 427 degrees Celsius. Krafla last erupted in the 1980s during the so-called Krafla fires, so the magma was always there, waiting. The drill simply found it. And if molten rock can surprise us, so can something that should have been dead for 250 million years. Number 4. The Resurrected Bacterium. In the year 2000, a paper in Nature made a claim so extreme that scientists are still arguing about it. Russell Vreeland, William Rosenzweig, and Dennis Powers reported that they had revived a living bacterium from a salt crystal about 250 million years old. If true, that organism would be older than the dinosaurs, by far the oldest living thing ever brought back. The bacterium was labeled strain 2-9-3 and dubbed Bacillus permians. It came from a fluid inclusion, a tiny pocket of trapped brine, sealed inside a crystal of rock salt. That salt belonged to the Salado Formation in New Mexico, which dates to the Permian period, roughly 250 million years ago. The crystal itself was recovered from a borehole near the Waste Isolation Pilot Plant, the deep nuclear waste site. Inside that ancient droplet, the microbe had survived as an endospore, a dormant, armored survival capsule that bacteria form when conditions turn hostile. The team knew the obvious objection would be contamination, so they surface sterilized the crystal before drilling into the inclusion. Even so, the criticism came hard. Russell Doolittle and others pointed out that the bacterium's DNA looked almost identical to modern relatives. Over 250 million years, they argued, the genetic code should have drifted far more. Either the sample was contaminated by a modern microbe, or the salt had recrystallized more recently than its surroundings. The defenders pushed back. The sterilization protocol was strict. Salt fluid inclusions really can trap brine and microbes for immense spans. And perhaps, some suggested, a dormant cell repairs its DNA slowly even while sleeping, which would explain the modern look without contamination. This is where the three theories sit. The mainstream skeptical position says the age is unproven and contamination is likely. The pro-revival camp, rooted in the study of salt-loving extremophiles, says ancient life can endure far longer than we assumed. And at the fringe, you will hear it framed as near immortality. Life that simply does not die so long as it stays sealed. The work built on an earlier and equally contested claim from 1995, when scientists said they had revived bacteria from a bee trapped in amber. What makes strain 2-9-3 matter is its push into astrobiology. If dormant cells can ride out 250 million years inside salt, then the salt deposits of Mars become a place to go looking for sleeping life. From a single sleeping cell, we leap to something vast. Drilling has also pulled up entire continents. Number 5. Zealandia, the drowned 8th continent. We are taught that Earth has 7 continents. Drilling helped make the case for an 8th. It is called Zealandia, and it covers nearly 5 million square kilometers in the Southwest Pacific. The catch is that about 94% of it lies underwater. Only its highest ground breaks the surface, as New Zealand and New Caledonia. The rest is a hidden landmass, drowned beneath the sea. The argument that Zealandia is a true continent was laid out in a 2017 paper led by Nick Mortimer of GNS Science. But an argument needs evidence, and the decisive evidence came from drilling. That same year, International Ocean Discovery Program Expedition, 364's sister effort, Expedition 371, sent the research ship Joides Resolution to drill cores across the Lord Howe Rise, a key part of submerged Zealandia. They pulled up roughly 1,250 meters of sediment at several sites. Inside those cores were fossils that should not be there if the region had always been deep ocean. They found shallow water organisms, and even pollen and spores from land plants. That meant parts of Zealandia were once above sea level, with beaches and forests, before they sank. The cores also recorded major changes in geography tied to the birth of the Pacific Ring of Fire, letting scientists reconstruct how subduction began in the western Pacific around 50 million years ago. Zealandia's story starts with the supercontinent Gondwana. About 80 million years ago, Zealandia rifted away, stretching thin as it pulled from Australia and Antarctica. Its continental crust thinned to somewhere between 10 and 30 kilometers, thinner than a normal continent, and most of it slipped below the waves. Tiny fossils called foraminifera in the cores allowed precise dating of each sediment layer, turning the drowned land into a readable timeline. The mainstream geological view says Zealandia meets all 4 criteria for a continent, and the drilling sealed the case. There is a genuine scientific debate about definitions. about where exactly the line between continent and large submerged block should be drawn. And at the fringe, the idea of a sunken land feeds older myths of lost continents like Lemuria, even though the science describes a slow tectonic drowning, not a sudden disaster. In 2023, a refined map of Zealandia was published using dredged rock and core data. An entire continent hid under the ocean, and only drilling could confirm it was real. Sometimes, though, the cores prove that a whole sea simply disappeared. Number 6. The Mediterranean Salt Giant. In 1970, the research ship Glomar Challenger was coring the floor of the deep Mediterranean as part of the deep sea drilling project. What the scientists Kenneth Sue and William Ryan pulled up did not match a seafloor at all. Instead of normal marine mud all the way down, the cores held thick layers of evaporate minerals, gypsum, anhydrite, and rock salt. These are the minerals you get when a body of water dries out. The conclusion was staggering. The Mediterranean Sea had once almost completely evaporated. The event is now called the Messinian Salinity Crisis, and it ran from about 5.96 to 5.33 million years ago. The cause was tectonic. The Strait of Gibraltar, the narrow gateway to the Atlantic, closed off. Cut from its main water supply and sitting in a hot climate, the Mediterranean began to evaporate faster than rivers could refill it. It shrank into salt flats and shallow, hypersaline lakes. The scale is hard to absorb. Roughly 1 million cubic kilometers of salt was deposited across the basin. In places, the buried salt layer is more than a kilometer thick. The deep basins may have dropped thousands of meters below normal sea level, becoming a baking, salty abyss. At the peak, this single event locked away around 6% of all the dissolved salt in the world's oceans. Then, it ended, violently. The Atlantic eventually breached Gibraltar again in what is called the Zanclean Flood. Water poured back in at a rate that may have reached 1,000 times the flow of the Amazon River, and the basin may have refilled in only months to a few years. The cores show this directly. Deep sea mud sits abruptly on top of the salt, marking the moment the sea came roaring back. Scientists even found stromatolites and shallow water fossils on what is now the deep basin floor, along with layers of wind-blown desert dust from the dried-out years. The mainstream model is straightforward desiccation, a sea cut off and evaporated. There is a long-running debate about whether the basin dried as a deep empty canyon or a shallow series of lakes. And catastrophist readings dwell on the sheer drama of the Zanclean Flood, one of the largest floods in Earth's history. Similar buried salt giants lie beneath the Red Sea and the Gulf of Mexico. A drill core proved an entire sea had vanished and returned. And in the oil fields of Canada, a drill operation hauled up something that still looks alive. Number 7. The Suncor Nodosaur. This is the most literal oil drill find on the list. On March 21st, 2011, a shovel operator named Sean Funk was working the Suncor Millennium Oil Sands mine near Fort McMurray, Alberta, digging through rock to reach the bitumen below. His machine struck something strange and hard. It was a dinosaur, and not just bones. It was one of the best preserved dinosaurs ever found, so complete that it looks less like a fossil and more like a sleeping animal turned to stone. The creature is a nodosaur, an armored plant eater related to the ankylosaurs, but without the tail club. It lived about 110 to 112 million years ago, in the early Cretaceous. In 2017, it was formally named Borehole Mark Michelli, honoring Mark Mitchell, the technician who spent something like 7,000 hours painstakingly freeing it from the rock. The result is often called a dinosaur mummy. What makes it extraordinary is the soft tissue. The fossil preserves skin, its armored plates called osteoderms, and the three-dimensional outline of its body. Most dinosaurs survive only as flattened bone. This one kept its shape. By analyzing preserved melanin, researchers reconstructed its color. It was reddish-brown, and it showed countershading, darker on top and lighter underneath. That detail is telling. Countershading is camouflage used by hunted animals, which means that even an armored, tank-like creature weighing well over 1,000 kilograms still feared large predators. The preservation reached inside the animal. Its stomach contents survived, revealing its last meal, mostly fern leaves, which shows it was a selective browser rather than an indiscriminate grazer. There was even charcoal in the gut, evidence that it had been feeding in a landscape recently swept by wildfire. From the plants, researchers narrowed its death to late spring or early summer. How did it preserve so perfectly? The oil sands region was a shallow seaway in the Cretaceous. The Nodosaur's bloated carcass likely floated out to sea, then sank and landed on its back in the soft marine mud. Marine minerals rapidly encased the body, locking in fine detail before it could rot. The specimen weighs about 1,300 kilograms as preserved, and in life, the animal was around 5.5 meters long. It is now displayed at the Royal Tyrrell Museum in Drumheller. The mainstream science is taphonomy, the study of how things fossilize, and this is a textbook case of rapid marine burial. There is real debate about how confidently we can reconstruct ancient color from melanin, and there is a cultural tension worth noting, the strange fact that one of the greatest fossils of the century was found by an industry digging for oil. Speaking of holes dug for the wrong reasons, none is more famous than the deepest one ever drilled. Number 8. The Kola Superdeep Borehole. In 1970, deep in the Soviet Arctic on the Kola Peninsula near Murmansk, engineers began drilling a hole purely to see how deep humans could go. Over nearly 2 decades, the main branch, called SG-3, reached 12,262 meters by 1989. That is more than 12 kilometers straight down. It remains the deepest artificial point on Earth, and astonishingly, it penetrated only about a third of the way through the continental crust. The project was a quiet scientific counterpart to the space race, a contest to reach inward rather than outward. And like the space race, it produced surprises. The first was heat. Geologists had expected temperatures around 100 degrees Celsius at the bottom. Instead, they hit roughly 180 degrees Celsius. At that heat, the rock began to behave plastically, almost like putty, and the borehole walls deformed and squeezed shut. Drilling equipment failed constantly. The deeper discoveries were genuinely strange. At about 6 kilometers down, in rock around 2 billion years old or more, the team found microscopic fossils, around 24 species of ancient plankton, preserved not in limestone, but in carbon and nitrogen compounds. They found free-flowing water at depth, where there should have been none, apparently squeezed out of the minerals themselves under crushing pressure. They detected hydrogen gas so abundant it made the drilling mud appear to boil. And the expected boundary deep in the crust, the place where granite was supposed to give way to basalt, never appeared. The rock stayed granitic and shot through with fractures far deeper than the models allowed. The bottom rocks date to about 2.7 billion years into the Archean eon. The borehole also gave the world a famous piece of folklore. The well-to-hell legend claimed Soviet scientists had lowered a microphone and recorded the screams of the damned. It is a complete hoax, but it shows how the idea of drilling into the deep earth grips the imagination. The mainstream value is pure geophysics, direct data on the composition, temperature, and behavior of the deep crust, much of it overturning prediction. The genuine puzzle that still invites discussion is biological, microfossils in water far deeper than expected. And the fringe, of course, keeps the screaming well alive. The hole was abandoned in the 1990s and sealed with a welded metal cap, only about 23 centimeters wide, a small rusted lid over the deepest wound humans ever cut into the planet. Other drills aimed not at depth for its own sake, but straight into a global catastrophe. Number 9. The Chicxulub crater core. 66 million years ago, an asteroid roughly 10 to 12 kilometers across slammed into what is now Mexico's Yucatan Peninsula. It carved the Chicxulub crater and triggered the mass extinction that ended the age of dinosaurs, the KPG extinction. The crater is now buried, hidden under rock and sea. In 2016, a drilling expedition went straight into it to recover the rock record of the worst day in the history of complex life. The mission was International Ocean Discovery Program and International Continental Scientific Drilling Program Expedition 364, co-led by Joanna Morgan of Imperial College London and Sean Gulick of the University of Texas. Working from a small lift boat platform called the Myrtle in shallow Gulf waters, they drilled into the crater's peak ring, a circle of mountains inside large craters, and pulled cores from down to about 1,335 meters below the seafloor. The cores answered long-standing questions. The peak ring turned out to be granite, rock uplifted from deep in the crust, confirming that during the impact the solid crust briefly behaved like a fluid, sloshing and rebounding in a matter of minutes. The samples were full of shocked quartz and other signatures of shock metamorphism, the fingerprints of an impact. They confirmed the dynamic collapse model of how giant craters form. The most haunting result came in a 2019 study. A section of the core preserved what happened in the first day after impact. There were rapid layers of melted rock and shattered breccia, then evidence of tsunami backwash sweeping debris into the crater, and charcoal carried in from the wildfires that the impact ignited across the region. You can hold in a single core a record of hours that erased most life on Earth. Sulfur-rich rocks at the site help explain the catastrophe, because the impact vaporized them into sulfate aerosols that blocked the sun and plunged the planet into an impact winter. The mainstream view is the impact model, now strongly confirmed by this drilling. There is an ongoing scientific debate about how much the contemporaneous Deccan volcanic eruptions in India added to the extinction, and fringe ideas float multiple impacts. The cores also recorded recovery. Microfossils just above the impact layer show that life recolonized the crater surprisingly fast. Within years to millennia, a flicker of hope at the top of the worst day in deep time. The final entry on our list is gentler to look at, but in its own way, just as dangerous. Number 10. Methane Hydrate, the fire ice. Imagine pulling a lump of ice from the seafloor, holding a flame to it, and watching it burn. That is methane hydrate, and the nickname is fire ice. It is methane gas trapped inside a microscopic cage of frozen water molecules, a structure called a clathrate. It forms only under high pressure and low temperature, which means it sits mainly in deep seafloor sediments and in permafrost, hidden across the continental margins of the world, often a few hundred meters below the seabed. The numbers are remarkable. A single cubic meter of methane hydrate can release something like 160 to 180 cubic meters of methane gas. The total carbon locked in hydrates worldwide may exceed all other fossil fuel reserves combined. When drilling and coring reach these layers, they routinely bring up chunks that fizz, hiss, and melt the instant they leave the deep, because hydrate is unstable at surface pressure and falls apart fast. That instability is exactly the danger. Methane hydrate is a serious drilling hazard. If a well disturbs it, sudden gas release can rush up the borehole and cause a blowout. Researchers have linked hydrate behavior in the riser pipe to part of the 2010 Deepwater Horizon disaster. On a larger scale, hydrate breakdown is suspected in ancient seafloor landslides, like the enormous Storegga slide off Norway, which sent a tsunami across the North Sea in prehistoric times. There is deep time written into fire ice as well. A massive release of methane hydrate may have helped drive the Paleocene-Eocene thermal maximum about 56 million years ago, one of the sharpest global warming events in the geological record. Because methane is a potent greenhouse gas, Scientists watch hydrates carefully today as a possible climate feedback, the so-called clathrate gun hypothesis. Yet it is also being chased as a resource. Japan's national program achieved the first offshore production test in the Nankai Trough in 2013. China extracted methane from hydrates in the South China Sea in 2017, and again in 2020. Dedicated scientific expeditions have studied hydrate systems directly, and seafloor seeps of hydrate host thriving communities of tube worms and clams that live on chemistry, not sunlight. The mainstream view treats hydrate as resource geology, a vast and difficult energy frontier. The climate science view raises the clathrate gun, the fear of runaway methane release. And the speculative voices imagine fire ice powering nations. It is energy source, geohazard, and climate wildcard, all in one strange, burning lump pulled from the deep. Across all 10 of these finds, a single uncomfortable pattern keeps repeating. To understand why drilling keeps surprising us, it helps to see how far the technology has come. It began with shallow water wells and grew into rotary oil drilling, the spinning bit and pipe that defined the 20th century. In the 1960s, the ambitious Mohole project tried and failed to drill clear through the ocean crust into the mantle, but it lit the path. Out of that ambition came scientific ocean drilling, a chain of programs that put research first rather than profit. The Glomar Challenger and later the Joides Resolution turned ships into floating laboratories that could core the deep sea floor anywhere on Earth. Japan built the Chicxulub, a riser drill ship designed expressly to reach the mantle. On land, continental scientific drilling programs sank holes into craters, fault zones, and volcanoes. The tools matured along the way, diamond-tipped bits, engineered drilling mud to cool the bit and hold the walls, and core barrels that capture an intact cylinder of rock or sediment rather than grinding it to dust. Depth, it turns out, is limited less by length than by heat and pressure. As Kola showed, the deeper you go, the hotter and softer the rock becomes, until the hole itself deforms. Boreholes stay narrow and fragile, sometimes only a handful of centimeters wide, kilometers down. To study deep life, crews add strict sterilization and contamination controls because a single modern microbe can ruin a billion-year-old sample. Remotely operated seafloor drills and real-time logging tools now send data up from places no human will ever stand. Mining boreholes, drilled for metal and oil, double as accidental science access. Each rig, in the end, is a kind of time machine, and the deep biosphere stayed invisible to us until these machines went looking. 3 of the items on this list point to the same astonishing idea. Life is not confined to the thin skin of the planet we live on. Estimates suggest the deep biosphere, the realm of microbes living inside rock and sediment, holds a vast share of all the microbial life on Earth, perhaps rivaling everything on the surface combined. The devil worm, the microbes in 2 billion-year-old water, and the contested salt bacterium all belong to this hidden world. Down there, life runs on chemistry instead of sunlight, a strategy called chemolithotrophy. Hydrogen from radiolysis becomes food. Some of these organisms may divide only once in centuries or even millennia, living so slowly that the line between dormant and dead almost dissolves. In 2020, researchers led by Yuki Morono revived microbes from seafloor sediment about 100 million years old, cells that had been barely ticking over since the age of dinosaurs. Endospores and deep dormancy are how such longevity is possible. The implications reach past biology. If life thrives kilometers underground here, then the most promising places to seek it elsewhere are not sunlit surfaces, but buried ones. The subsurface of Mars, the oceans beneath the ice of Europa, and Enceladus. The central challenge is always contamination, proving that what you pulled up was truly down there and truly ancient. Every new borehole seems to push the depth record for life a little deeper, and raises a quiet ethical question about disturbing ecosystems sealed away since long before humans existed. There is, quite literally, a second biosphere beneath our feet, and we are only beginning to read it. The same is true of the rock itself, which turns out to be a kind of archive. A drill core is the closest thing we have to a book of Earth's history, written in stone and read from top to bottom. In undisturbed layers, depth roughly equals age, so a single core can carry tens of millions of years within a few hundred meters. Sediment layers record time, sometimes year by year. Microfossils like foraminifera and plankton act as precise clocks, letting geologists date each band with confidence. Different layers tell different stories. Evaporate beds, like those from the Mediterranean salt giant, record vanished seas. Impact deposits, like the Chicxulub core, capture a single catastrophic day, complete with shocked quartz, melt rock, and charcoal. Pollen and spores, like those in the Zealandia cores, preserve lost landscapes of forest and shoreline. Isotopes record ancient climates, and even in trapped water, the passage of 2 billion years. The thin clay of the KPG boundary appears in cores and outcrops around the world, a single global timestamp marking the death of the dinosaurs. What makes these archives so powerful is that they turn inference into direct evidence. We do not have to guess that the Mediterranean dried out or that a continent sank. The core shows it in hand. There is something deeply unsettling about holding a piece of a day that happened 66 million years ago, or a film of water older than multicellular life. Cores are also irreplaceable. Each one is a non-renewable sample, a unique extraction from a place we may never reach again. They have rewritten textbooks more than once. And yet, for all we have pulled up, the deepest parts of our planet remain firmly out of reach. For all this, a humbling fact remains. We have never drilled through the crust into the mantle. Not once. Kola, the deepest hole ever made, reached only about a third of the way through the continental crust before heat defeated it. That is the recurring barrier, not distance, but temperature, with pressure close behind, crushing and deforming boreholes until they fail. The Mohorovicic discontinuity, the MOHO, the boundary between crust and mantle, has never been drilled despite decades of effort and the purpose-built Chicxulub. Most of the deep biosphere has never been sampled. The great salt giants and the drowned continents have been touched by only a handful of cores, pinpricks in something planet-wide. Cost is a constant limit, since each deep hole is enormously expensive and samples only a single point. Magma systems remain almost entirely unexplored from within, the Iceland strike being a rare accident rather than a plan. The true depth limit for life is still unknown, and every new expedition that finds an extremophile redefines what habitable means. There are real technology gaps for the ultra-hot deep zones, places where current tools simply melt or seize. In some respects, we have mapped the surface of Mars in finer detail than the rock a few kilometers beneath our own feet. The next generation of deep drilling, including efforts to finally reach the mantle and to drill back into magma on purpose, aims to close that gap. Until then, the planet keeps most of its interior to itself, and that is worth sitting with. Look back across these 10 finds, and one trait unites them. Every single one surprised the people who pulled it up. Drilling began as a search for ordinary things: water, oil, metal, heat. It became, almost by accident, a window into deep time. Crews looking for gold found an animal living in the rock. A team chasing minerals tapped water older than complex life and tasted it. Engineers drilling for steam struck molten rock, and a search for salt revealed that a whole sea had once dried to dust. A shovel digging for oil uncovered a dinosaur so perfect it seems to sleep. A core from a buried crater preserved the worst single day the Earth has known. And lumps of ice from the deep sea floor turned out to burn in the hand, holding both the promise of energy and the memory of ancient climate upheaval. The common thread is the unexpected. the reminder of how little of the world beneath us we actually know. The deep Earth is the last great frontier, harder to reach in places than the surface of another planet. Every borehole is a gamble and a revelation, a thin needle pushed into immense darkness. These discoveries make the scale of geological time suddenly tangible, something you can hold in a core or watch flow from a pipe. They reshape our sense of where life can exist and where our own moment sits in the long story of the planet. The ground beneath your feet is not solid, silent, and empty. It is an archive that resists being read, full of fire, water, salt, and sleeping life, waiting for the next drill to reach a little deeper and surprise us all over again. Somewhere on the Kola Peninsula, a small rusted cap still seals the deepest hole we ever made, and beneath it, the planet keeps its secrets.